So we are recording now, and I'm going to share my screen. So we're going to finish chapter 22. Let's see. No, we're going to finish chapter 21. 21 is start chapter 22. So I have to adjust this schedule here. I don't think we're going to be able to cover both of them. And let's leave it this way right now. There's just one more section to cover in chapter 21. And this section is how we calculate the magnetic field, okay? That's the important, we're not gonna cover 21.9. Not gonna cover 21.9, and I go. Going back here to my notes. Okay, and let's material for the second exam. So copy here and paste here. More students coming in. Okay, so far the exam is going to be on this Wednesday. Are you ready for Wednesday? Think about that if you're ready for Wednesday. Let's take a look here at the schedule again. Should be, should be the day after tomorrow. Let's see. Oh, you're not ready yet? Okay. Anybody else? Anybody else? I'm willing to change the date of the exam for next week, okay? I'm willing to do that because we have plenty of time between exam 2 and exam 3. Think about that. If you want me to change that, we can do it next Wednesday. I think it's even better because we still have to finish covering chapter 21, right? So Zenobi, yeah. Okay, think about that, and okay, good. Let's hear from more students, right? And then before the end of the class, we make a decision, okay? Oh, so far we have 13 students only, right? Okay, and so he go material for the second exam. Let's go through the chapters 21 sections, right? Magnetic field 20.1. The force that a magnetic field exerts on a moving charge 20.2. Motion of a charged particle. You can see my screen, right? Here's the book chapters, and are my notes. Okay, 20.2. Did I say? Oh, wait a minute. I'm looking at the wrong one. This one here. Okay, here you go. 20.1, electromotive force and current. That's 20.1 is all about. Ohm's law, 20.2, resistance and resistivity, skip temperature dependence, 20.4 electric power, 20.5 alternating current just with a resistor. Later on, we're going to see other devices connected to a circuit as an alternating current, 20.6 series wiring, resistors connected in series, right? Resistors connected in parallel wiring, and then a combination of parallel and series, resistors in series and parallel. We're skipping internal resistance. 20.10 is Kirchhoff's law, very important. Kirchhoff rules, measurement of current and voltage. Okay, 20.12 capacitors in series and parallel, and RC circuits. Okay, this chapter is has lots of materials. This chapter here, lots of material. And then chapter 21, magnetic fields. Okay, right now, at the beginning, we just said that there's a magnetic field. There are some stones, naturally occurring stones that generate a magnetic field. Okay, and 21.2, the force that a magnetic field exerts on a moving charge. You get those stones, those load stones. Okay, and we can show that the magnetic field exerts a force in a moving charge. The motion of charged particle in a magnetic field, and the mass spectrometer. Within 21.3, we talked about the velocity selector as well. 21.5, the force on a current in a magnetic field. Yeah, which is similar to the force of to a magnetic force on a moving charge. What you see right in here is similar to what you have right in here. Okay, why is that? Because a current is nothing but a moving charge, several moving charges, right? So this chapter comes naturally from this section comes naturally from the other section. We talked about the torque in the current carrying coil. Why did we do that? We did that because it has an important application in electrical motors. You pass a current through a loop, subject that loop to a magnetic field, and you can make that loop rotate over and over again, provided you change the direction of the current at the right time, at the proper time. Magnetic fields produced by currents, okay, and that's the source of magnetic field. The source of magnetic field is an electric current. So far, up to here, we didn't say how magnetic fields are produced, but the reason magnetic fields are produced is not because of the lodestone. It's something far more basic than that. The reason magnetic fields are produced is because the charges are moving. Moving charges produce a magnetic field. Moving charges, which are current, produce a magnetic field. Okay, and finally, we're going to cover Ampere's law. We're not going to cover this one. We're going to cover Ampere's law right now. Okay. So let's just okay. The source of magnetic fields is an electric current. You pass. This is a law of physics. This is a physics law. You pass a current through a wire. How do we do that? By connecting the wire to a battery. And while there is a current flowing in the wire, comma, there is a magnetic field associated with it, with this current. Okay. And what else you have to remember? B fields circulate around a current carrying wire. Okay, if you remember the difference between the fields, magnetic fields, and whereas E fields radiate, circulates around the source of the field, circulates around the current carrying wire, which is the source of the field. What about electric fields? Electric fields radiate from an electric charge, which, by the way, is the source of the field. That's the difference between electric fields and magnetic fields. What we are going to see now is how to calculate a B field for a given current distribution. Okay, so let's write that down here, right? See whether you want to postpone the exam to April, would be 19, right? Right now, yeah, it would be the 19th. Right now, the exam is scheduled for, right now, the exam 2 is scheduled for April 12th. Think whether you want to postpone the exam to April. Okay. So you calculate the B field using Ampere's law. Okay, that's how you do it. So let's rewrite the laws. You write the laws of E and M. One more student. Gauss's law, which is nothing but Coulomb's law in a different format. Coulomb's law in a different format. Okay. And mathematically, how it looks like. Mathematically, it looks like that. Should be the electric flux, okay, equal to Q enclosed divided by epsilon naught. Okay. But the Q enclosed the Q enclosed by a Gaussian surface. Okay. Let's not forget that the electric flux is nothing but the electric field parallel to the vector area. I don't like it. This one here. Not good. Parallel. Let's put parallel to the vector area. Let's see, parallel. Can I do another one? I don't think you let me do. Yeah, you won't let me do Oh, let me do. Here you go. Parallel to the vector area of the Gaussian surface. Okay. You know, E stands for electric field parallel to the vector area of the Gaussian surface. Okay. The other law that you should know, we didn't solve any problems with the second law, okay, but it's important for you. Gauss law for electricity. Okay, Gauss law for magnetism. It's going to be the magnetic flux, which is nothing but the magnetic field parallel to the vector area, and what goes on the right side is the zero. This equation means that there are no magnetic charges. That's what it means. And then we have the magnetic force law or Lorentz law. Magnetic force law, which is QB the sine of theta, where the theta is the angle between the velocity vector of the electric charge and the magnetic field. Okay, 1, 2, 3. Okay, the direction of the magnetic force is given by the right hand law. How do we call that? Is right hand. We go right hand rule. Right hand rule. Okay, RHR. And now, next, what we have next? We have Ampere's law. Ampere's law. That was chapter section 21.8. Okay. It's 21.8. Ampere's law. Okay. And notes right in here. Another law of physics. And how do you formulate? Let's take a look at the equation of on the book, so you can stay. So you have the same. Okay, here you go. Here's the equation. Okay. When I forgot. Let's see here. Yeah, it should be a summation here too. Okay. Should be a summation here as well, just like we have a summation there. So summation of all. Sometimes we have just one surface, right? One Gaussian surface. Sometimes we have 2 or 3 Gaussian surfaces, okay? We did examples in which we had 3 Gaussian surfaces. That was the most number of Gaussian surfaces that we had as an example. Okay. Here's an area. Here's an area. Okay, Gauss, and here's the same thing, right? We gotta put a summation here. Can be 1, 2, 3. You know, that's what the book means. Magnetic field that goes through area 1, right? Magnetic field times the area, right? Plus the magnetic field 2 that goes through area 2, plus blah, 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 right? Now we have something similar for the Ampere's law. I'm going to use this one, but it's going to change somewhat. It's not going to be the magnetic flux anymore. Okay. Yes, it's going to be the magnetic field parallel, but it's not going to be parallel to the area. It's going to be parallel to, delta, to the path. It's going to be parallel to the path. Okay. If in the previous 2 laws, okay, if in the previous 2 laws, I'm going to elaborate on that. We calculated the flux of the electric field, and B field. In the previous law, we took the flux of the electric and B fields. In this law, we calculate the there's no, we don't call it a flux. We calculate the, let's see, the summation between the let's see, we multiply, let's do it this way. We multiply the B field by a given path, okay? And what I mean, we begin given path, a given end. And sum everything. Oh, by the way, it's not 0, okay? It's not 0 here. What should be, and like I said, it's going to become going to be mu naught times the current enclosed by the path. When I start making drawings, you're going to understand what I actually mean. Okay. Magnetic field parallel to the path times the length of the path is going to be equal to a constant times the source of magnetic field. Compare that to the other one, to Gauss's law of electricity. Right? Compare that to Gauss's law of electricity. The difference here, the only difference here, we have a field here, right? Is one field, here is another field. We have a source of the field, and here we have a source of the field. We have a constant related to the field, and here we also have a constant related to the field, right? The only thing that differs is that it's not an area, but it's a length of a path, okay? That's what the only thing that differs. Just like for the electric field, you know, we may have 1, 2, 3, even n paths, but here we're going to restrict ourselves to 3 passes only. Okay, so you can see how we apply that law. You know, compare the above to Gauss's law for the electric field. Ooh. Gauss's law for the electric field. Okay. That's the one. Right. I'm going to spell that out. We have a summation sign in both cases. In both cases, we have, here you go. In both cases, we have. So if you, what I mean that if you memorize that, it's not going to be difficult to memorize this one, right? In both cases, we have one, a summation sign. 2, a field. 3, a source for the field. 4, oh, important, right? Both sources are enclosed by the, what do I call that? By a geometry, by a geometrical figure, right? Geometrical figure. Both sources are enclosed by the geometrical figure. Okay, in both cases, we have a summation sign, a field, a source for the field. Both sources are enclosed by a geometric figure. The only difference, what else? In both cases, we have a constant, right? One is the magnetic constant, the other is the electric constant. One is a magnetic constant, the other is an electric constant. And the only difference being that you multiply the field for a pass, that in one case, the only difference being, in one case, you multiply the field by a pass, you multiply one field by a pass, right? You multiply the B field for the length of the pass, and in the other case, you multiply the E field by an area. Okay, that's the basic difference. In a way, this one is not different from the current because they are both sources of the field. Okay, I can argue that this one is not different from the other constant in the sense that one is a constant for the electric, for the field, and that both are constants for their respective field. Here we have the field itself, right? And what's differ is what is multiplying the field. Let's do some examples. Okay. Examples how to calculate the magnetic field. I already showed to you how to calculate the electric field, right? How to calculate the magnetic field now. First one. First, infinitely. Example 1. Infinitely long wire, right? Carrying a current I. Okay. Before we go to this example, let me give you a simpler example. Okay. Yeah. Okay. So before we go to an actual example, before we go to this one, let me give you another. I'll put that this one example one, example two, right? Example one. You know how to determine the path, right? One example here I have here in this slide. No? This one right in here. Okay. Ampere's law. Current enclosed by a loop. Okay. Suppose I'm going to do it this way. Suppose that we have 3 currents flowing. Okay. Current 1, 2, and 3, right? Example 1. Suppose you have 3 currents. I1, I2, and I3. I1 and I2. I1 and I2. I1 and I2 flows towards you, right? And I3 flows into the plane, flows away from the plane towards you, right? Yeah, okay, into the plane of the screen. And that's what we have right here. I1 pointing towards you, I2 points towards you, right? And I3, the current is flowing into the plane. Okay. If I go ahead and choose by Amperian loop, for instance, okay, in this way here, you can see, the same way that I choose a surface, right? Here is a loop, it's not a surface. You can see that this loop is not enclosing any of those currents, okay? Any of those currents whatsoever. Okay. So in the case of loop 1, it does not enclose any of the currents whatsoever. Consequently, I enclosed is equal to 0. Oops. Equal to 0. I'm gonna italicize this I here so it looks better. Italicize, italics, italics, italics. Okay, italics, italics. Okay, find, no, it's not how to determine the path. Find I enclosed. That would be better. Okay, find I enclosed for different loops. For different loops. Okay. 1. It does not enclose any of the loops, any of the current loop. The loop doesn't enclose any of the currents whatsoever. Consequently, I enclosed is equal to 0. Okay, that's what that I enclosed is all about. When you are solving a problem, you choose an appropriate loop, an appropriate Amperian loop, and then you determine how much of the current is enclosed by that Amperian loop. Okay, that's now let's take a look at another example. This is loop 1. That's loop number 2. Okay. In the case of loop number 2, the counterclockwise direction. Okay. In the case of loop 2, no, not this one here. In the case of loop 2, it encloses all 3 currents. Okay. If we choose the direction of the loop as being so there are those details, right? Counterclockwise, comma. Okay, here you go. Counterclockwise. Here you go. My right hand rotates in the counterclockwise direction, and my thumb points in the current I1 and I2. And it's contrary to I3. In this case, the I enclosed, okay? Consequently, here you go. The I enclosed is going to be what? I1 plus I2 minus I3. Make sense? I have to write that down here. I1 plus I2 minus I3. Let's take a look at another example. Let's see here. Let's look number 3. Yeah. What about if I change the direction of the loop? Instead of a counterclockwise loop for loop number 2, I come up with a loop number 3. Let's go in a clockwise direction, right? So all you have to do is to invert the signs, okay? In the case of loop 3, in the case of counterclockwise loop 3, right? In the case of clockwise loop 3, it encloses all the current. It encloses all the current. In the case of counterclockwise loop 2, it encloses all 3 currents. Consequently, okay, I don't need any of that. Consequently, I enclose is going to be I1 plus I2 minus I3. In the case of loop 3, that's a clockwise direction. It also encloses all 3 currents, but the enclosed current is going to be a minus sign than what we had before. Okay, make sense? Simple, right? And we can go for another example. Let's see this one here. I went ahead, come up with a loop number 4. It's still clockwise. Loop number 4, clockwise, encloses only I1 and I2. Okay. In the case of clockwise loop 4, it encloses only I1 and I2. It encloses only I1 and I2. It encloses only I1 and I2. Consequently, right? All 3 currents. All 3 currents. Consequently, I put consequently here, right? Consequently, is minus I1 minus I2. Okay, so that's the first piece of information that you have to know whenever you are dealing with the Ampere's law. Okay, when you're dealing with that, that's what I enclose is all about. You have to choose a loop, you have to choose the direction of a loop, and you have to identify how much of the current is enclosed by a loop, that loop. Okay. So in order to find I enclosed, so in order to find I enclosed, you must one, choose an appropriate loop, choose a direction for this loop, clockwise or counterclockwise, counterclockwise or clockwise. Okay. Calculate the net current according to the right hand rule. Okay, that's the procedure. That's how you find I enclosed. Okay, now we are going to go for an actual example. We're going to go to an actual example. Infinitely long wire carrying a current I. Okay.
Professor?
Yeah.
We have a classmate in the waiting room.
Oh, really? Okay, thank you. Here you go. Sometimes I don't hear those rings there. Thank you, Kennedy. One more, right? Here you go. Ampere's law. Now we are going to calculate the actual field. We just the first step was just to calculate the current enclosed. Okay. First step is just to determine the current enclosed by a loop. Now that you already know how to do that, we are going to calculate the actual B field. But we are going to do the simplest of all problems that they are going to see out there. The infinitely long current carrying wire. Power lines can be considered infinitely long, can be considered infinitely long current carrying wire, power lines, those lines that you see suspended by towers, right? They can be considered a very good approximation for infinitely long current carrying wire. And how do you define whether it's infinitely long or not? Well, it's the diameter of the wire. If the diameter of the wire is much smaller compared to its length, it can be considered infinitely long wire. Okay, so here you go. First step, illustrate your current flowing here in this slide, right? First step. Solution, right? One. Illustrate your current. Your electric current. 2. Check if the problem, just like before, check if the problem has symmetry. If it doesn't have symmetry, forget it. You cannot solve this problem using Ampere's law, using this technique, okay? Cannot. If the problem does not have symmetry, you cannot use this technique. You cannot use this technique. Okay, and then move on and cannot solve the problem using this. You cannot solve the problem. You cannot solve the problem using this technique. Okay. In this case, an appropriate loop, we call it Ampere's loop, right? Ampere's loop. Imaginary, right? An appropriate imaginary. Don't forget, this is an imaginary loop. It's just a mathematical tool that we use to solve problems. An appropriate imaginary Ampere's loop would be a circle centered at the current. Okay, so that's what you're going to see in the next slide. Here you go. Here's my circle. I'm going to leave the direction for the next slide, right? In the next step, see the appropriate loop, and I'm going to write that down. Radius R, an appropriate loop a circle of a radius R, centered at the current. Okay. And I'm going to go to the next step. Here you go. I'm going to show the radius R of this loop, of this Ampere loop. Don't forget, this guy is just a imaginary loop, is just a mathematical abstraction that we use to solve the problem. This one, hey, that's okay, leave this way. Radius R. I get a better. This one is better, right? Interesting. So strange. Oh. Circular Ampere loop coincides the. Let's see here. Not the coincides with the. Circular Ampere loop coincide with the center of the current. Center of the circular Amperian loop. Here goes. Center of the circular Amperian loop coincides with the current. Okay. That's what I have to fix here. And I don't want this one. I gotta, oops, this one. Okay. And then what I want next? I want this one here. Yeah. Yeah, I want this one here. And I gotta fix this other one here. Here you go. Center of the circular Amperian loop coincides with the current. Next, we have to choose the direction of the loop. I don't need that anymore. I don't need that anymore, so I can erase it, make it simpler. And now I'm gonna put the direction of the loop. Let's see, this one. Too small. Huh. Yeah, they put here, but it's so small. Maybe I should increase it here. 5. Yeah, okay, better, right? Counterclockwise. I choose counterclockwise. Better, okay. Counterclockwise loop. Do to the due to the symmetry of the problem. Okay. 4, next step. 4, choose direction of the loop, either clockwise or counterclockwise, either clockwise or counterclockwise. It's advisable, it's advisable. It is advisable, although it's not, must, it's advisable to choose a direction according to the right-hand rule. Right-hand rule. And that's what I did here. The palm of my hand rotates in the counterclockwise direction, and my thumb points in the direction of the loop. It's advisable to do that. And now we go the next step. Okay, we start solving our problem. Notice that we have a single pass, and the single pass is a circular pass. If I were to apply, apply Ampere's law. Ampere's law. Okay. Notice that we have a single pass because it's a circle, because the loop is a circle. Okay, so let's go there, right here. Apply Ampere's law. Here we go. N is going to be 1. In this case, N is equal to what is going to be 1. And we are going to have just, B, times delta L. I'm not going to put 1 there subscript because it's redundant. Okay. So it should be the magnetic field that's parallel to that path that you saw. So the question that you have to solve is this one here. Okay. And now let's analyze the problem. Okay, B. Continue numbering. Okay, good. Okay. Analyze in a qualitative way. Now, obtain the direction. Obtain, the direction of the B field in a qualitative fashion. Okay. So, applying the right-hand rule. Okay. Remember that. Remember that the B field circulates around the current, right? Going back here. So I want to put this guy right in here. Oops, right in here, better, right? Here you go. So you can see the arrow more clearly. Okay, so here you go. The B field circulates around the wire. I'm gonna and that's what I mean by finding out in a qualitative fashion what would be the B field. Here you go. Because the B field circulates around the wire and the pass is centered in the wire, it's reasonable to state that the B field must be tangent to this circle. Okay? We're going to write it down. Okay, because the Amperian loop is a circle with a centered at the current wire. Come on. It is reasonable to state that the B field will be tangent to the pass, okay? And will be counterclockwise as well. And one more thing, because every B field is at the same distance from the source, right? Source of the B field, the current, then it also implies that B1 is going to be equal to B2, the magnitude, by the way. It also implies that the magnitude of all those fields that you saw there are going to be equal to each other. B1 equal to B2 magnitude. Notice that I put before. Here you go. B1 equal to B2 equal to B3 equal to B4. Okay. Having said that, no matter where you are in the circle, you're going to have the same value here, the same value here, the same value here. Okay. So the same value, let's say, the same numerical value, right? The same scalar value, although the vector is different. Okay, so here we go. So we go ahead and apply. Let's see, here you go. We have this one here. Because the B field is the same, and the B field parallel to the path coincides with the B field as well, right? What we have to do, all we have to do, is to look at the length of this path. What's the length of this path? That's what delta L is all about. It's going to be 2 pi r. So we are almost over with this problem. Okay, what I didn't do here is to, substitute I enclosed by I. Okay, I was given, and we can finally solve this problem. That's the simplest problem you're going to see out there. Okay, for solving for the magnetic field, it's going to be 2 pi r. It decreases with the distance. The magnetic field decreases this with the distance. 950 right now. Okay, and I want to do, let's see, one more example. But before we go for another example, let's see which one I'm going to do here. I'm going to do for the solenoid. I'm going to skip this one. Okay, because it's going to take too much. But it's similar, like we did for the sphere uniformly charged, or the cylinder uniformly charged in its cross section. Okay, similar. So what I'm going to do is we're going to do this one right here. But before we do that, let's take attendance and take a break too. Okay, so I went it through in a very detailed fashion. I'm going to put like that to something else. I'm going to call that B. Oh. B right in here. Okay. Now, let me take attendance now. Randy Bautista, are you there?
Yes, I'm here.
Okay. Okay, good. So now I'm gonna ask you, do you wanna postpone the exam or you wanna do the exam on the day after tomorrow?
I think postponing would be better so we could all have time to study.
What did you say?
I think postponing would be better since we could all have more time to study.
Okay, postpone, okay. We can do that because we still have, some time for the third exam, okay? Let's see, we might not be able to postpone the third exam because if we do that, we'll be too close to the final, okay? I want you to understand that. So I don't think we'll be able to postpone this date here for the third exam, but it's okay to postpone this one because we're gonna have, let's see, 1, 2, 3, 4 weeks. It's a pretty good time. Okay, postpone. So I'm gonna ask each one of you whether you want to postpone or do the exam this Wednesday, okay? Vanessa Bodilla, are you there? Yes, okay. Do you want to postpone the exam, Vanessa? Postpone, please. Good. Next, Ashley. Ashley Diaz. I don't see Ashley here, right? Next, Natalie Espinosa. Postpone, yeah. Janet Garcia. I don't see Janet. Okay. Noor. I see Noor here. Yeah, do you want to postpone it, Noor? Janet. Okay, good. Looks like Janet just joined us, right? Can you hear me, Janet? I'll get back to Janet. Okay. Blanca Hernandez. I don't see Blanca. Okay, okay. Do you want to postpone the exam, Janet? We're discussing whether to postpone the exam or not to the next week. Yes, okay, good. Remember, we won't be able to postpone it again, right? From the not just the third exam, but once we set for next week, the second exam for next week, we won't be able to postpone it again, otherwise it becomes too close to the third exam, right? Blanca, are you there? I don't see Blanca. Okay, Kaylee. Postpone or not, Kaylee? Yes, okay. Most of you. Let's see. I'm gonna put like yeah, this way. Joshua. I don't see Joshua. Alondra.
Present.
Yeah, wanna postpone it, Alondra?
Yeah, I would like to postpone it.
Okay. Kennedy.
So, yes, I'm here.
Do you want to postpone it?
I agree.
Okay, good. Daisy? Yes, doesn't matter to me. Okay. Okay. I'll put blank here. Yesenia? Okay, do you want to postpone it, Yesenia? Yeah, okay, good. Ryan on. Good. Artur Pacheco? Yeah, postpone or not? Yes, okay. Lady Lud?
I'm here.
Okay. Postpone it?
Postpone it. Yes.
Okay. Most of you, right? Donia?
Here.
Yeah. Want to postpone it too, Donia?
Yes.
You said yes?
Yes.
Okay, good. Thank you. Elika?
Here,
Yeah. Postpone it or not?
absolutely.
Okay, absolutely. Okay. I don't think the spring break was enough for me to, to rest, Maybe it was the same, it's the same with you all. Okay, Brianna? Yeah, okay, thank you, Brianna. And Justena? Okay, good. So let's almost everybody. Okay. 17, 18, good. So let's break, right? Break between 10 a.m. and 10:15 a.m. Any questions before we move to the break? Okay, if there's no question, I'll see you in 15 minutes. I'm back here, and let's adjust here the schedule now. Gonna go here to the 19th. So we are going to have lab 6. Don't forget, now lab 5 is due, right? This we're changing. And what's going to change here? Let's see. South down, and this one goes here. This one goes here. And black. And see. Let's see, 24. No, wait a minute, what am I doing here? 19. Oh. Let's see. Insert. Cells. Shift cells down. Okay. Okay, now we're in good shape. This one goes here. This one goes here. Begin induction. Okay, I don't think we're going to be able to do that. So let's put that here. And '23 and '24. Lead cell up, go up. Now, what's going on here? 20. Oh yeah, this one should be 20 lab. Okay, lab 6. I will, maybe we do some chapter 22 as well. Okay, and delete. Okay. Yeah, so that's version 14. I will save that as a PDF as well. And Okay, so that we are set here. And this one. Because we're moving the lab to Wednesday, I would rather if you turn in lab 5, okay? Let me know if you can make it. And alternating current circuits, electromagnetic. Okay, good. So electromagnetic induction. Good. And let's finish chapter 21 so we can get into electromagnetic induction. That's the only thing that's missing here. And I'm going to go very quickly through this one here, okay? I'm going to go very quickly through this one so you're not at loss with it at all. It's now what we did here was the case of a one-dimensional wire that has no dimension whatsoever, no cross-section whatsoever, right? But what if the wire has a cross-section? And what if the current is uniformly distributed throughout this cross-section, okay? What is delta I divided by delta A here at this point is the same as delta I divided by delta A here, and so on, okay? It's a problem similar to that other one that we did for the sphere, uniformly charged, for the uniformly charged sphere, and also for the uniformly charged cylinder. It's similar. With a different formula that you use a different formula, okay? But don't forget, here you're going to have less current than if you were to calculate throughout the whole cross section, okay? If I is the net current that flows throughout the whole cross section of the circuit, here that is my Amperian loop, the amount of current that flows within this Amperian loop is going to be less. Okay, and I'll do that quickly, and I'll just set up. I'm not gonna finish. Okay, so here you go. Find example 2, right? You find infinitely long wire. Example 3, infinitely long wire of radius R carrying an uniformly distributed current I, net current I. The net current through the cross section of the wire is I. Okay? Find B field for R less than big R. Okay? And what you're going to do, for lowercase, here you go, solution. For R greater than big R, the B field is the one we calculated previously. Okay. It's just like, why is that? Okay, because we're going to have an Amperian loop. I don't have an Amperian loop here. Here you go. I'm gonna put it here for you. The Amperian loop is going to encompass the whole wire. And I'm gonna put this guy sent to the back. Yep. It's going to encompass the whole wire, the whole cross section of the wire. And the problem, ends up being the same as what we did for the previous one. Okay. I have to shrink it a little bit. Okay. R greater than big R. I'm going to put it here. Yeah. I hate that. big R. Okay, go. No, less. This one is less. Less than big R. And then I'm going to use that in the other one. Here you go. Whoa. This one is small. Okay, let's see. Greater. Good. What about here? What about here? In this case, don't forget the key here is uniformly distributed current. Because the current is uniformly distributed, this problem does have symmetry. It has cylindrical symmetry. So we use a circle centered at the center of the current carrying wire. If you were to use this circle here, it wouldn't have symmetry. You couldn't solve the problem for this specific loop, okay? But if you center the cylinder, if you center the curve at the center of the wire, then now you do have symmetry, geometrical symmetry, and you can solve the problem. But now the key here is to find out how much current you have right in here in this area, okay? There's a little trick for this one. Okay. For R less than big R, we must define a current density. Okay, we must define a current density given by, usually abbreviate, we usually, call this current density by the letter J. It's going to be given by delta I over delta A, which is the area. Delta I by the delta A, because the current is uniform, because the current is uniformly distributed, through the cross section of the wire, This J can also be here written. And by the way, I think I'm going to put A prime here, okay? I'm going to put A prime. Yeah, it's better. We put A prime is going to be equal to the net current divided by the net area of the wire. The net current is I, is given by the problem. The net area is going to be pi capital R square. Okay. And now we have J is equal to this guy here. And now we want to find out how much current we have in this small circle that you see right in here, the Amperian circle. So here we go. And my unknown current is going to be this delta I. And my area, my A prime area, right, is going to be pi R squared, but it's going to be the lowercase r, the genetic R. Okay, it's going to be like that. And now solve this equation for this delta I. The pi goes away, right? R squared ends up here. And that's how the current changes with a given Amperian loop. The given Amperian loop. Okay, and that, by the way, is going to be my enclosed current. My current enclosed by the loop. That's the one. We know R, we know big R. R, this lowercase r, is just the distance from the center of the wire. And we go back to our, equation that we saw before, right? This one right here. B2 pi r is just a single pass. 2 pi r, my I enclosed is going to be this value here. And now we are ready to solve this problem just like we got for, let's see if I'm forgetting anything. No. Right? These R cancel out with this one of those two R's. And we pass the 2 pi to the other side. 2 pi R. Where? I like to put this B naught there upstairs. And that's how the B field behaves. For R equal to 0 at the very center of the wire, the B field is 0. So there is no current flowing there. It's just as though as you had came up with a impedance loop of radius 0. Okay, but as the radius keep on increasing, as the radius of the impedance loop keeps on increasing, the B field also keeps on increasing. Okay? And we go ahead, do the right-hand rule, and the B field circulates around the current, the direction of the current. It keeps increasing linearly. Let's see if it makes sense. Okay, I've noticed that at small r equal to big R, what happens? The above equation reduces to, reduces to that. Which, by the way, coincides with this result here that we got before. For small r equal to big R. Okay? So the B field is, we say that the B field is the same. Okay, it gotta be the same. Okay, that's one. There is another one that's very important. Okay, this one here for the solenoids. This one is important, folks. This one you have to know how to do it. Oh, everything is important. Everything that we do here is important, but this one is even more important than the other ones. Why is that? Okay, the reason is that there are lots of devices like this one that has practical applications. Okay, the solenoid, you can use a solenoid for a valve. You can to let water and stop water passing through a pipe. Okay, there's something that we call solenoid valve, and there are devices called contactors. It's also a solenoid. Different ways of applying the same device. This device is so important that the symbol for the inductor is the solenoid. You're going to see later on. Okay. So what the question that we make here, let's look there at example number 3, right? No, example number 4 now. What we want now, here, example number 4. Find the B field of a solenoid of radius r, length L, and turns. And by the way, I'm going to make a condition here, very important condition. Otherwise, the L is much greater than R. Okay, and turns and current I. Okay. Solution, right? Okay, the solution for this problem is a mix of qualitative and quantitative results. It's a long problem to solve, okay? It's a long problem to solve, but we're gonna do that. It requires extensive drawings to understand all the details of the behavior of the B field. Okay. And I'm going to walk through. Here you go. That's how it looks like my solenoid. You get a tube, okay? You get a bunch of wires, wind it around it, and connect to a battery. Without the battery, there is no magnetic field. The current flows like that in this direction. And I want to know what's going to be the magnetic field outside the solenoid and inside the solenoid. Okay, what you're going to find out is going to be a very interesting result. Let's see if I can get a solenoid there in the internet so you can see how it looks like. Little solenoid. See that solenoid valve, 12 volts? I bought a bunch of those because I was doing some experiments. Let's see. Okay, here you go. That's how it looks like. See, that's the solenoid. An illustration of the solenoid. You can put it around the tube, or you can have a wire that's rigid enough that would support itself, okay? That's the solenoid. We want to find the magnetic field of the solenoid. Let's see, let's take a look at the solenoid valve. Solenoid valve, 12 volts. There is a solenoid valve, 24 volts as well. Here you go. Let's see where, yeah, the solenoid valve, in this case, I don't like those illustrations. We should have a better one. I want something more familiar to me. Let's see if I can find it. Well, what's happening here is that this device, the solenoid valve, managed to interrupt the passage of the water here, right? Just by applying a magnetic field. That's it's built in such a way that allows you to do that. You pass a current, it closes. It turn off the current, it opens. Okay. Water solenoid valve, 12 volts. All the drawings there. Unfortunately, do not have a simulation. Let's see if they have a simulation out there. Solenoid valve simulation. Let's see if they have out there. It would be nice to. Let's see, simulation proportional solenoid valves. Let's see if this one works well. Okay, modeling simulation. Okay. Let's see. Needle. Let's see. That's the part of the solenoid valve, right? There's a needle here. Plunger. Those are the circuits. I don't know. I don't like this one. Let's see. Let's start at the beginning here. Okay, we see that this device moves back and forth. All right. Sometimes it closes, sometimes it opens. Okay. Let's see if we have a better one. I don't like this one here. Solenoid valve. Maybe this one here.
Hi, this video is about solenoid valves. There are many different makes and types available. but this video is give you the concept that how solenoid valve works. Okay? As you can see, as this power
Yeah, here you go.
on,
I like this one.
okay, so this is a simulation here. So if you can see here, so right now, okay, so as you can see, as this power turns on,
Yeah.
this solenoid, this cylinder is lifted, and then it flows here, the fluid. Again, this is.
So what we have? We have the pipe here, okay? Water can flow through this region, but right now the valve is closed. Okay, right now the valve is closed. The solenoid was activated, and a plunger, right? A plunger forced this device right here just by turning on the current in this circuit. This guy here can be a metal. And here is my solenoid. Okay, here's my solenoid. When you turn off,
this cylinder is going up, and it's making the opening here, and it passes through. So this is how the
okay, here's oh man, let's go slowly.
Guys, okay, so this is a simulation here. So if you can see here,
yeah, right now the circuit is closed. Okay, let's see.
So right now, okay, so
when you open the circuit, no current passes through it. Okay, the valve closes. And so what's happening here? What's happening here? Okay, let me explain exactly what's happening. If there is no current passing through the solenoid, there is no magnetic field here inside. This plunger here basically is a metal plunger. If there is no magnetic field, this guy is not attracted towards the solenoid, okay? When we turn on the current, the plunger is attracted towards the solenoid and let the water flow through the pipe. So this is the device that opens and closes the pipe, okay? Again, when you turn on, when you pass current through the circuit, in this specific case, okay, the valves open. When you turn off this circuit,
this solenoid, this cylinder is lifted, and then it flows here.
The water flows. When you the circuit is closed, is opened, okay, then the magnetic field of the solenoid goes to 0, and the plunger is moved back to its initial position, okay, and closes the passage of the water. That's basically how the solenoid valve works. And let's go through the derivation of this, of the magnetic field of this device, okay? So you have to picture that. You have to picture that you have, you know, wires wound around this. It doesn't have to be a cylinder, okay? Because if the wire is rigid enough, you can keep it in that way that you saw in the picture, right? Now, here's another drawing how you should visualize the current flowing through that helical path, right? So the current is coming out of the board here, which is the upper region here of the solenoid, right? It's the current flows down all the way here, and when it reaches this point, the current goes into the board. Okay, that's how we should visualize. Okay, the first thing that you have to do is to look at a single wire. You know, just concentrate in the single wire right in here, and you already know. For a very long wire, you already know that the magnetic field circulates around this wire, right? And look at the direction. I put the direction in the proper way, okay? So let's start documenting there. So you have, okay, the B field of our solenoid, okay. So first, visualize the current around first visualize a wire a wire around a tube. Okay. Pass a current through this wire. 3. Indicate the directions of the current on the top portion of the solenoid and bottom portion, on the top and bottom portions of the solenoid. On the top and bottom portions of the solenoid. Indicate the direction of the current on the top and bottom portions of the solenoid. That's what I did that in my drawing. Okay. Visual, draw, not visualize. Draw, here you go. Let's put draw a wire. Draw the magnetic field around a single wire, right? That's what I did there. I got a single one of those wires here and drew the magnetic field around it. And then you fill it with the second one, right? And now we have, the magnetic field around those two. Something interesting happens when you put one next to each other. Look what happens. The magnetic field of this wire is in this spot is going to be upwards, but the magnetic field of this other wire at this spot is going to be downwards. Consequently, those two fields are going to cancel out. Make sense? That's what happened. That's the qualitative part of the derivation of the solenoid. There's no other way of solving that I know of. There's no other way of solving the magnetic field of the solenoid other than that. And by the way, that's not in your book, okay? And now we're going to put a third wire there, right? And look what happened. Same thing happens. Magnetic field of this third wire cancels the magnetic field of the second wire. Okay. And if you have several of those wires, we're going to end up having almost no magnetic field in the vertical direction, with the exception to the very last wire there in the solenoid. Okay. So for the bulk part of the solenoid, we have no magnetic field in the vertical direction. By the bulk part of the solenoid, what do I mean? In this region here, in the middle, we have only magnetic fields in the horizontal direction. No magnetic field in the vertical direction. Okay. That's why the length of the solenoid should be very long compared to the radius. So what we discover, okay? Let's write that down there. Draw the magnetic field around a single wire. Indicate the direction current at the top of the bottom. Let's see. Get a single wire. Draw a single wire, right? Draw a single wire. And with a single wire, draw the magnetic field around it. It should circulate around it. Place a second wire next to the first one and draw the magnetic field as well. Note that the vertical component of the B field cancels out in between these two wires. Okay. No, doing for n wires, we notice that the B field is mostly in the horizontal direction, right? Mostly in the horizontal direction. Horizontal here to the left, horizontal here to the right. Is circulating around those wires. Then we did that for the top wires. We did this one for the top wires that coming out from the board. Let's do now for the bottom wires. Okay, in this case, the current is into the board. Okay, so put the B field in the proper direction. Is rotating around the current. Okay, place another B field, place another wire next to it. Notice that the vertical component of the magnetic field cancels out, just like before. Third one, and so on, right? At the bulk of the solenoid, again, the magnetic field is going to be only in the horizontal direction. The difference being is that here at the top of this wire is going to be to the right, and on the bottom is going to be to the left. Okay? Let's take a look here. That's what we got for the top wires, and that's what we got for the bottom wires. Notice that at the top of those wires is to the left, field is to the left. At the top of those wires, the field is to the right. But at the bottom of this one, the field is to the right as well. Okay? And then what else can we do? Okay, we can go ahead. Don't forget those fields, those magnetic fields stand away from those wires, right? So here you go. If I consider only the field from the bottom wires, those fields are extending upwards as well. They may or may not decreasing in intensity. They may. I put here that they're not decreasing intensity, but they may or may not. We're going to find that out later, not now. Okay. We have the same. Oh, and what else? Not only those fields here of those wires extend inside the solenoid. Let's see here what's going on. Yeah, it also extends above the top wires, right? Make sense? So here you go. I'm going to extend the field of those bottom wires right here, up all the way up. Not only extend within the solenoid, but they are also present right in here. And look what happens. These fields here tend to cancel out those fields here. Okay? And that's where an approximation comes about. Strictly speaking, this field here should have an intensity smaller than this field here, in principle, strictly speaking. But because of that approximation, that the length is much larger than the radius, it's very reasonable to assume that this field here has an intensity that's approximately equal to this one. Okay? So now we get this simplification in which we found that the field outside the solenoid is going to be zero, approximately zero, not zero, but approximately zero. Okay, and we do the same for the top wires. It behaves exactly the same way downwards. Okay, we extend the field due to those top wires. Below the bottom wire, this field cancel out the other field. See that? And we have something like that. So we have a concentration of magnetic field just in the bulk of the solenoid. Okay. So because this field here is adding up to the other one, I put a longer arrow, right? So here you go. Outside is approximately 0. Do you see how simple the solenoid is? Outside the solenoid, the magnetic field is 0. It's a behavior very similar to that of a capacitor. Outside the volume of the capacitor, parallel plate capacitor, the electric field is 0. Okay, I'm gonna write that down for you so you have time to absorb everything. Do it for any wire, do know, see that the B field is mostly in the horizontal direction. Okay. Pass indicated direction. Somewhere around the 2, pass it to the wire. With a single wire. With a single wire at the top of the solenoid. That's what we did, right? Draw the magnetic field around it. You should circulate around it. Place a second wire next to this first one. Okay. Repeat the steps 4 through 7 for the wires at the bottom of the solenoid. Okay. Okay. Extend the B field of the bottom wires upwards. Upward, just like I did. Okay, where am I right now? I am writing here. Oh, not here, sorry. I am writing here. Okay. Note that inside the solenoid, the B field of the bottom wire adds up to the B field of the top wires. On the other hand, outside the solenoid, the B field of the bottom wire cancels out the B field of the top wires. We can state, okay. Repeat steps 9 through 11 for the top wires. And we find a similar situation. As a result, we conclude that the B field inside the solenoid is much greater than the B field outside the solenoid. Okay? 14, because you're not going to see anything like that in books, okay? They never do the documentation in words, step by step. Because L is much greater than R, it is reasonable to state that the outside B field is approximately 0 or negligible compared to the field inside the solenoid. Okay, we didn't finish yet. There's more. Here is just the qualitative portion. And that's where we are right now. B field is approximately 0 on the outside, but the inside is not 0. And that's where the actual calculations come. Now we know that the B field is outside the 0, outside the solenoid is 0. What do? Now we choose an appropriate loop. Okay? We already know that the field here outside is 0. We know that the field here inside is not 0. Amperian loop. Choose here. Choose a square loop at the top, can be at the bottom as well, of the solenoid. A rectangular, not a square, a rectangular loop at the top of the solenoid. I'm going to choose a rectangular Amperian loop. I'm going to put that Amperian loop at the top. The Amperian loop has 4 sides, 4 paths, right? Now we have this problem in which we have 4 paths for our loop. 1, 2, 3, 4. Let's see how I label them. Here you go. Now I'm coming up with a zoom, right? I'm zooming into that Amperian loop. I'm choosing, choose a rectangular Amperian loop at the top of the solenoid. Amperian loop has 4 sides. Has 4 sides of 4 paths with a horizontal length equal to a width on the horizontal length equal to L. I do not know what this L is. Okay. But I don't need to know. You're going to see why is that. Okay. Apply Ampere's law for all these 4 arms. And now we're going to do the actual calculation. Here you go, right in here. Don't forget, I have already chosen the direction of my loop. My loop is in which direction? It's counterclockwise direction. I choose the counterclockwise direction because this path here is parallel to the B field inside. That's why I choose it. Okay. When I multiply the B field by this path length here, you're gonna get a positive number. If I had done clockwise direction, the multiplication between B and this length would end up being a negative number. So it works like that. So don't forget there's a parallel 1, 1, delta L1. Parallel, 2, delta L2. Parallel, 3, delta L3. Parallel 4, delta L4. Let me put another step here so we shouldn't, let's see, I think I can do, yeah, I have to change it here, 4, from 1 to 4, because it's 4 different paths. Okay. Remember that we saw that, let's see. But don't forget, this parallel means what? This parallel means parallel to the direction of the path, okay? This path is in the vertical, and we learned that there is no vertical. Sorry. Start with the number 1. Okay, this path is in the horizontal, And we do know that there is a horizontal component of the magnetic field along this direction, right? So we can go ahead and write, B, that would be B1, right? We do not know what B1 is yet. L1 would be L, capital L. Okay. I wrote that down, B1. What about the B2? Do you have a component of the magnetic field parallel to this direction here? This direction is vertical, right? There is no vertical direction of the magnetic field. Consequently, the second term here is going to be 0. There is no parallel component of the magnetic field along that direction. What about here in the horizontal direction? It is the horizontal direction. And we found out that the magnetic field outside the solenoid is approximately 0. It's negligible. So we can neglect this one as well. Here you go, 0. Finally, we have the last arm in the vertical direction. Because of the vertical direction, there is no vertical component of the magnetic field. We also have 0. And now we have to worry about the I enclosed. The Amperian loop is enclosing those many wires. Okay, I'm going to call it N. Okay, let's see, I'm going to call N prime. N prime, because I use N for something else, right? Times I. I don't need that. Right. Okay, I erase this guy here. There's one more thing that we can do. Okay. And then there's a mathematical trick here. Note that I told you that the solenoid has a total of N turns. Let's see here, length. I shouldn't be using this length here. I'm just going to, I'm going to use here L prime, okay, to distinguish from the length of the solenoid. Very important, very important. L prime. And I have to adjust there here to L prime, to distinguish from the length of the solenoid. Okay. Okay, and I'm going to do something else. I'm going to rewrite this formula as like that. Okay. I'm passing the L prime to the other side. I do not know what N prime is. I do not know what L prime is. L prime is an arbitrary value. Okay, but I do know. No, I do know that I do not know what N prime is. I do not know what N prime and L prime are, but I do know what N and L are. I also know that the wire was uniformly wound around the tube. Okay, you go. So here you go, and that find the B field of the solenoid radius cylinder. Let's put that here. The wire is uniformly wound around the tube. Find B field. Find the B field. Okay, it doesn't have R less than big R. It doesn't have to be. Find the B field everywhere, right? Everywhere in the solenoid. The solenoid R less than big R and R greater than big R, like that. Okay, I do not know what N prime, but because the wire was uniformly wound around the tube, what does it tell us? it tells us that n prime n prime divided by L prime is equal to n divided by L. We usually denote this one by lowercase n, density of wires. Okay? And look what we end up getting. We end up getting that the magnetic field inside the solenoid is going to be given by this. I'm going to put this right here. I'm going to just take out the n prime because we know n, right? And we know L. And we can rewrite that as n like that. Very important. Very important. Mu naught is a constant. This guy here is also a constant. And this guy is also constant. It doesn't change. There is no other geometrical parameters here. Okay? And by geometrical parameters, I mean what? Like the distance of this wire to anywhere here inside the solenoid. It's not dependent on the distance of each of those wires to the center of the solenoid. Okay? The above means that the solenoid, the V field of the solenoid, is uniform. It does not change its intensity. Here you go, its intensity does not change with the distance from the wires themselves, from the wires. Okay, very important. So we can write it down like that, you know. I'm going to write it down, the final solution here. B field of the solenoid is equal to okay, this one that I want is equal to mu naught Ni for lowercase r less than big R, and is approximately 0 for what happened here? I want to erase this one. I want to erase this one as well. Good. For R greater than big R. Okay. The electric counterpart of the solenoid is the parallel plate, the uniformly charged parallel plate. In this case, the field is uniform inside the volume of the capacitor and 0 outside it. Okay. Uniform, remember? Okay. And 11:15 now. Any questions about that? Now we're done with chapter. We're done with chapter 21. Now I want a different one. We're done with chapter 21. We're done with chapter 21. And now we start chapter 22. But first, do you have any questions? So we're gonna have our break now. Let's do that 11:15 a.m. to 11:30 a.m. Okay. And don't forget, the solenoid is a very important device. We use that in MRIs. MRIs have a bunch of solenoids there inside. It's very important that you learn that if you want to understand how MRIs work. And not just MRIs, but other devices as well. Okay, we have solenoids in our car. We have solenoids in water circuits, in pipes, right? We use solenoids to open and close the flow of water by controlling it electrically. We can program it to do that. We have microcontrollers out there. If you people play with Arduino, for instance, right? I do not know if any of you do that. You know, there's those Arduino microcontrollers. They're very popular. We can use those Arduinos to control our solenoid valves, for instance, okay, or even the contactors. That's how important the solenoid is. It has lots of applications, okay? And if you don't have any questions, I'm going to stop my recording here, pause my. I'm back here. And okay, so that's how we we find out the magnetic field inside a solenoid, okay? So just do the right-hand rule. There's another way to use the right-hand rule as well. You know, the other way to use the right-hand rule in a more straightforward way is to rotate your palm around the direction of the current, of the flow of the current. You rotate your palm around the direction of the flow of the current. Your thumb will indicate the direction of the magnetic field as well, okay? There's another way of finding that out. We can do the same thing for the toroids. I'm not gonna do that here. Try to figure out on your own too, how to apply the Ampere's law to determine the magnetic field in the toroid. The toroid is a donut shape, okay? Magnetic field here in this region is going to be 0. The magnetic field outside this region is also going to be 0, but not inside the toroid. Outside the toroid, the magnetic field is 0 because this current here cancels out this other current, right? The enclosed current is going to be 0. The magnetic field here is also equal to 0 because there is no current flowing in this region. Okay, that's toroid. And what we're going to cover now is the law of electromagnetic induction. Okay, very important. You know, that's the basis. The law of electromagnetic induction is the basis of today's technological society. If it weren't for that, we wouldn't have electricity, okay? Because batteries by themselves is not enough to feed the whole country. Batteries alone is not enough. We need something else other than batteries. And what we need electromagnetic induction. We need generators. Most of the electricity that we get doesn't come from batteries. Most of the electricity that we get comes from generators. And generators are governed by the law of electromagnetic induction, which is chapter 22, right? Oh, not here. This one? Chapter 22. First, I am going to give you a qualitative understanding. We are not doing, you know, magnetic materials, okay? We're skipping that. Why is that doesn't go there? It's so strange, this book. Sometimes it works, sometimes it doesn't. Let me see if it. Okay, okay, good. Electromagnetic induction, and I'm going to illustrate that for you. You can also read the book here and look at the illustrations in the book. It's all about generating current. Chapter 22. Chapter 22, electromagnetic induction. Induction. That's something that what I'm going to tell you is something that we do observe. Let's take a look at YouTube. Let's see if they have any electromagnetic induction. Magnetic induction. See if they have any videos about that, so you can understand. That's something that we can, that I always do in my face-to-face classes there at the college. We have a bunch of demonstrations that I like this one. Here's the solenoid. See a solenoid here? Okay. We have those solenoids there. Let's click this one. I like this one better. Okay, let's skip that. Okay, electromagnetic induction. There are several ways of what does it mean, electromagnetic induction? Let me write that down here for you. What does it mean? Electromagnetic induction. Okay, what does it mean? Oh, it means the following. It means that we can induce, it means that we can induce an electric and magnetic field by means other than using a battery. Okay, the easiest way to understand, but it's not the complete way to understand. Okay, the easiest way to understand it is, although it's not the whole story, okay, although it's not the whole story, okay, there's more to it, is that we can induce an electric current in a circuit without a battery. Okay, that's what it means. But strictly speaking, in a more complete sense, is that we say that we can induce an electric and magnetic field, not just an electric. Magnetic field comes later on by means other than using a battery. Okay, I'm going to illustrate that for you. Oh, let's go to the YouTube first. And okay, here you go. Here's my solenoid. Okay, here's my solenoid. Is a solenoid with square cross section. That equation that you saw, the uniform magnetic field applies to any geometrical configuration of the solenoid. Okay, so we have the end of the wire, one end of the wire here, the other end of the wire is here. So we have this bunch of turns here around this tube, right? And it starts here, the wire starts here, apparently goes like twice around it and ends here. What you see right in here is an ammeter. It's a device that measures current. Analog, it's an analog ammeter. It's not the digital one that we use. Notice that it can measure up to microamperes, right? All the way 30 microamperes, their highest value that it can measure, from 0 to 30. One is positive, the other is the flow of current in the negative direction. What this guy is going to do, remember, this is a solenoid, a bunch of wires wound around a tube. What this guy is going to do, he is going to show to you that we can produce a current just by using a magnetic field. but it's a magnetic bar. Okay, and you know, see, this is a magnet. He's inserting the magnet inside this tube. Look at the needle of the ammeter. Okay. And now notice that the guy is at rest. The magnet is not moving, and the current is 0. The magnet must be moving for you to induce a current. The faster the magnet moves, the stronger the current. Okay. While the magnet is at rest, there is no induced current whatsoever. Okay. You can do that with a magnetic bar, but you can also do with a current flowing through another circuit. You can get a second circuit that flows a current. That current, you know, generates a magnetic field, and that magnetic field can maybe used to induce a current in a second circuit. Okay, so here's another loop. There is no battery here in this loop. Here you go, the other ammeter, right? It's a very cheap ammeter, this one here. Okay, he inverted the polarity of the magnet, and now the current should flow in the other direction. Let's say it again. Here you go. That's another solenoid, this one. 0.5, right? Hey, wait a minute. Let's go. Let's watch it again. Good, here. Okay, one polarity is north, the other is south. Okay, blue and red, they are different polarities. 1.4. He's measuring, he's measuring current. The knob here is indicating the current. He's not measuring voltage. When he withdraw, the current is negative, right? Insert, current is positive. Withdraw, current is negative. It's very, now he's inverting the polarity. Now he's inverting the polarity. He's inserting with a different polarity, and the current is negative. Withdraw, the current is positive. Insert, negative. Withdraw, positive. Now what he's going to do now? Let's see what he's going to do now. Oh, okay. What he's going to do is the following. Here, remember this solenoid that he initially had. Now he has two solenoids here, okay? He has two solenoids here. The outer solenoid is connected to a battery. What you have here is a resistor, okay? So what he's going to do, he's going to pass a current through this solenoid, and he's going to insert the second solenoid inside the other one. The second solenoid has no power whatsoever, has no battery whatsoever. It's connected to this multimeter. When people discovered that, it was something really, unexpected. It was so many applications that we have nowadays because of this phenomenon. Okay, let's play. Ammeter. Okay, he's turning on and turning off, okay? Turning on and turning off. He has a switch in there. When he turns on momentarily, what's happening? When the current is zero, what's happening here? When the current is zero here inside in the solenoid, the magnetic field, its magnetic field is also zero. However, the moment that you turn on the current builds up from 0 to a given value in a very small amount of time. That's the transient, okay? As the current builds up from 0 to a given value, the magnetic field inside the solenoid also builds up from 0 to a given value. That's a change magnetic field in time. Once the magnetic field reached its value, there's no more induction. That's why this guy is going back to 0. Okay, here you go. Turning on and off the circuit. Here the multimeter changing, right? And so let me just, so those things are actually exist. That's another way. Let me see this one here. Yeah, this one is another way of inducing. Okay, here. Okay, there's a solenoid as well. Okay. There is no battery. He's showing to you there's no battery in there whatsoever. It's just the wires wound around. I presume that this one is a magnet. He's not saying, but must be a magnet. Okay, he's gonna hook up this lamp to the solenoid. Remember, there's no battery whatsoever. And what he's doing here, he is completing the circuit. Okay, he's completing the circuit. Okay, do you see? This is a magnet indeed. Okay. Whoa. Oh, it's more than a magnet. This thing is more like an electromagnet. Okay, it's an electromagnet. You can see that the current increased, right? So let's skip this one. We have another one to that I see. I want to see a generator, okay? Generators. Generator simulation. Okay. I like this one. Okay, let's take a look.
In this module,
there are several ways of inducing a current.
Generator. An AC generator is an electric generator that converts mechanical energy to electrical energy.
Okay, let's take a look at that. Okay, we have our circuit here, wires, closed circuit. We have a magnet, north and south. Okay, you can induce a current in your circuit, and here is my ammeter, just by rotating this circuit inside a magnetic field. Okay, that's the principle of the generator there in your power station.
An AC generator works on the principle of electromagnetic induction.
You can do that. Electromagnetic induction with a magnet. You can do electromagnetic induction with a current that changes in time. You can do electromagnetic induction with a circuit that rotates. We're gonna go through that. Here you go.
When there is a relative motion between a coil and a magnetic field, an electric current or EMF is induced in the coil. Parts of an AC generator. An AC generator has an armature ABCD. It is a rectangular coil with many turns wound around a soft iron core. A shaft. It can be rotated rapidly. A field magnet. It may be a strong permanent magnet with concave poles. Two slip rings S1 and S2. These are connected to the armature and thus rotate with it. Two brushes B1 and B2. They provide electrical contact with the slip ring on a load, which may be a galvanometer and shown.
Here they are ammeter.
working of an AC generator. When the armature rotates between the poles of the field magnet, the magnetic flux linked with the armature changes continuously. As a result, an EMF is induced in the armature. This in turn produces an electric current through the armature and the galvanometer and through the split rings and the brushes. Note that the galvanometer needle swings between the negative and positive values. This means
This is the type of current that we get in our homes, okay? Far away there in the station, in the electrical station, power station, we have something like that, a device like that feeds a whole city, a whole region, and we get this type of current that changes direction and intensity back and forth. Okay, so that's okay. How can we induce a current in a circuit? Okay, there are one way to induce a current in a circuit is by approaching and receding a magnetic bar to a closed loop circuit. Okay. No need of a battery. No need of a battery. The important thing here is that the important point here is that the magnetic field is changing in time, okay? That's the important point here. That's one way, and it is illustrated, let's see. Yeah, right in here. Okay, here you go. What I have here is just a current loop, no battery whatsoever, just a wire, a copper wire, a closed copper wire, subjected to a magnetic field, add a magnetic field. If the magnetic field is constant, doesn't change in time, no current is induced in this loop. Okay, if you change the magnetic field by approaching and receding your magnet bar, then you do induce a current in the loop. Okay. So that's by approaching and receding a magnetic bar to a closed loop circuit. No need of a battery. Okay, the important point here is that the magnetic field is changing in time. Okay, another way is by having an electric circuit with a battery next to your closed loop without a battery. Circuit one, I'll call that circuit one. Circuit one, next to closed loop without a battery. That's the circuit two. When you switch on your circuit one, current builds up from 0 to a given value, right? This current also generates an associated magnetic field that builds up from 0 to a given value. In a small amount of time. During this short period, right? There be few changes and induces a momentary current in circuit 2. Okay, that's another way of doing that. Let's see here, and that's what we have here too, right? This magnetic field can be a magnetic field from a second circuit that's varying there. Okay, here is the magnet that you saw before. We connect an ammeter to the solenoid, approach the magnet. The magnetic field is going to increase, and you will induce a current in this circuit. Okay, here goes the other one that I mentioned to you. We have two circuits, circuit 1 and 2. One has a battery, the other doesn't. Okay, at this very moment, the magnetic field is 0 because the current is also 0. The magnetic field of this circuit is 0. The moment I close the circuit, the current builds up from 0 to a given value. The magnetic field follows the increase of the current. And in that very small amount of time that the magnetic field is increasing, you induce a current in the circuit close by. Okay, and what I want to do after some time that the current has been established in the other circuit, the induced current goes to 0. Okay, you still have a current flowing here. The current achieves a steady state value, which is constant in time. We still have a magnetic field, but the magnetic field is no longer changing here and it's no longer inducing the current. Okay, so that's what I documented there. Okay, number 2. Let's see if we can. Okay, there's another way. There's another way. There's more than 2 ways. There are 3 ways, okay? 4, I would say. You can also, you don't need the magnetic field that doesn't need to be constant. That doesn't need to be varying in time to induce the current in the circuit. Here's my circuit, okay? Which other way can we do that? Okay, we can change the area of the circuit. If we put the circuit to oscillate back and forth, okay? And that's my circuit here, okay? The magnetic field can be constant because the area here of the circuit subject to the magnetic field is changing. You are going to induce a current in the circuit as well. Okay, so 3rd way, 3, by changing the area of your closed loop circuit subjected to a constant magnetic field. We can have that too. Okay, so I shrink and expand the circuit. Okay, if I shrink and expand the circuit, you will be able to induce a magnetic field as well. Those are all the qualitative ways. Oh, there's one more. There's one more. You can also rotate. You can also rotate your loop in a constant magnetic field, and that's the most practical way of inducing a current. That's what you saw in that simulation. Okay, this simulation right in here. Okay, by rotating. 4, by rotating the circuit, a closed loop circuit, in a constant magnetic field. Constant magnetic field. So that's what scientists observed some time ago. We have 2 more minutes. I want to conclude very soon. Okay. If we put all of that together, okay, we can see that it's not just a matter of changing the intensity of the magnetic field. Okay. It's not just a matter of changing the area of the circuit that makes it make you induce a current. It's not just a rotation of the closed loop in a constant B field. Okay, when scientists look closely at those experimental evidences, what do they conclude? They actually conclude scientists, after looking at this here, after looking at all these experimental evidence, scientists concluded that the crucial parameter here was not the magnetic field alone. It was not the area of the circuit alone, but instead it was the magnetic flux. Magnetic flux, okay? So if the magnetic flux changes in time, you induce an electric current in a closed circuit. Okay, so that's the key discovery that scientists made. And that's another law of electricity and magnetism. And I'm going to elaborate a little bit more next time when we meet, okay? Remember, changing magnetic flux induces an electric current in a circuit. Any questions?